Welcome to my project bazaar. We are going to see the product for built-in self-test and digital calibration of 0IF RF transceivers. Next we are going to see the abstract for our product. The low-power programmable generator capable of producing pseudo-random test patterns with desired doggling levels and enhanced fault coverage ratio compared with the best-to-date built-in self-test based pseudo-random test pattern generators. It is comprised of a linear finite state machine, a linear feedback shift register or a ring generator is the finite state machine, driving an appropriate phase shifter, and it comes with a number of features allowing this device to produce binary sequences with pre-selected doggling activity. The method automatically selects several controls of the generator, offering easy and precise tuning. The same technique is subsequently employed to deterministically guide the generator toward test sequences with improved fault coverage to pattern count ratios. We propose LP test compression method that allows shaping the test power envelope in a fully predictable, accurate and flexible fashion by adopting the Presto based logic BIST infrastructure. The BIST is a design for testability technique that places the testing functions physically with the circuit under test. The test pattern generator generates the test patterns for the CUT. Examples of pattern generators are a ROM with stored patterns, a counter, and a linear feedback shift register. The logic built-in self-test, originally developed for board, system, and in field test, is now gaining acceptance for production test as it provides very robust DFT and is used increasingly often with test compression. This hybrid approach seems to be the next logical evolutionary step in DFT. It has potential for improved test quality. It may augment the abilities to run at speed power aware tests, and it can reduce the cost of manufacturing tests while preserving all LBIST and scan compression advantages. The conventional scan-based test hybrid schemes, due to the high data activity associated with scan-based test operations, may consume much more power than a circuit under test was designed to function under. With overstressing devices beyond the mission mode, reductions in the operating power of ICs in a test mode have been of concern for years. Full toggle scan patterns may draw several times the typical functional mode power, and this trend continues to grow, particularly over the mission mode's peak power. This power-induced overrest may result in thermal issues, voltage noise, power drop, or excessive peak power over multiple cycles, which in turn cause a yield loss due to instant device damage, severe decrease in chip reliability, shorter product life. The BIST can keep average and peak power below a given threshold. The test power can be reduced by preventing transitions at memory elements from propagating to combinational logic during scan shift. This is achieved by inserting gating logic between scan cell outputs and logic they drive. During normal operations and capture, this logic remains transparent. Gated scan cells are also proposed. A synergetic test power reduction method uses available on-chip clock gating circuitry to selectively block scan chains while employing test scheduling and planning to further decrease BIST power in the cell processor. Next we are going to see the flow diagram for our product. The advantages of BIST include the capability of performing at speed testing, very high fault coverage, elimination of test generation effort, and less reliance on expensive external testing equipment. The BIST techniques are classified into offline and online. Circuit under test. It is the portion of the circuit tested in BIST mode. It can be sequential, combinational, or a memory. Their primary input and primary output delimited. Test pattern generator generates the test patterns for the CUT. It is a dedicated circuit or a microprocessor. The patterns may be generated in pseudo-random or deterministically. Multiple input signatures register is designed for signature analysis, which is a technique for data compression. MISR efficiently map different input streams to different signatures with every small probability of allies. MISR are frequently implemented in built-in self-test designs in which output responses are compressed by MISR. A quest to achieve higher BIST fault coverage with shorter test application time generated an immense amount of research. The pseudo-random test sequences were modified either by placing a mapping logic between the peer-fuse outputs and inputs of a circuit, or by adjusting the probabilities of outputting zeros and ones so that the resultant vectors capture characteristics of test patterns for hard-to-detect faults. We use multiple architecture for the 16-bit output result in the DFT section. The architecture has built-in customizable flexibilities enabling the testing and diagnosis of entire memory subsystems. Finally, we are going to see the output for our product. Double click on the BIST project icon. We use Xilinx 14.2 version. Here we have to create the new project and save the new source into that project. The file consists of the main code. Then for the output we have to click on simulation, main, and then simulate behavior model. Once we simulate, the simulation will run in iSim. Here the control signals are reset and clock. We have to give the value for the reset. The reset initial value is 1. Then for clock, click on force clock, and then leading edge value is 0 and trailing edge value is 1. Period is 1000 nanoseconds. Then we have to run. Again for the final output we have to force constant value as 0 for reset. Then we have to click on run button. The address is indicated here and the data is indicated here. Then again click on run. The address will be in 3 bits and the data is 16 bits. Again click. So the data corresponding to the memory has no errors. This time the error has occurred, so the output FDS becomes 1. For pressing the run button again and again, the output 1 remains unchanged because of error. Again we have to reset. For reset give 1 and then enter, then again run. It will be reset. Then force constant and 0, then run. Here the memory and data will be matched, so the output is 0 because of no error. Then we have to see the RTL diagram and synthesis report. For RTL diagram and for synthesis report we have to click on implementation. Then implement design. Here the synthesis report is generated. Here the number of flip-flops used will be given and LUT. Then for the timing report we have to click on timing report. So here the timing will be given 2.336 nanoseconds. For RTL diagram we have to click on view RTL schematic, then main, add, create schematic. We have to double click on this, the architecture will be created. Thank you.